Light behaves as both a wave and a particle. Light is one of the most ordinary things in our daily lives, yet it hides one of the deepest mysteries in science. When physicists first began trying to understand what light truly is, they discovered something shocking. Light does not behave like just one kind of object. Instead, it behaves both like a wave and like a particle, depending on how we observe it. This strange dual nature sits at the heart of quantum physics and helps explain why Richard Feynman believed light cannot be fully pictured in the way we visualize everyday things. For centuries, scientists debated whether light was made of particles or waves. Isaac Newton believed light was made of small particles, which he called corpuscles. Around the same time, other scientists such as Christian Huygens argued that light behaved like a wave spreading through space like ripples on a pond. The argument seemed simple: either light is one or the other. But nature refused to play by these simple categories. When light was studied carefully, certain experiments showed clear wave behavior. For EXA, light bends around objects and spreads out when passing through small openings. This bending and spreading, called diffraction, is something waves do naturally. Sound waves bend around corners, water waves spread around rocks, and light behaves the same way. Another powerful demonstration came from interference experiments, where two waves overlap and create bright and dark patterns. These patterns only make sense if light behaves like a wave. By the 1800s, the wave theory seemed settled. Then new discoveries shook everything. When scientists studied how light interacts with matter, especially metals, they discovered something that waves alone could not explain. In the photoelectric effect, light shining on certain materials can knock electrons out of atoms. But this only worked when the light had a high enough frequency, regardless of intensity. Increasing brightness without increasing frequency did nothing. This suggested that light carried energy in tiny packets, not as a smooth, continuous wave. Albert Einstein solved the puzzle by proposing that light comes in discrete packets of energy called photons. A photon is like a tiny bundle of energy that behaves much like a particle. When light strikes metal, it is not a wave washing electrons away, but individual photons hitting them like miniature bullets. This discovery earned Einstein a Nobel Prize and introduced the particle view of light into physics again. The real mystery appears when we combine both ideas. Light is not sometimes a particle and sometimes a wave in a simple switching sense. Instead, it behaves according to rules that blend both descriptions. In some experiments, it clearly spreads and interferes like a wave. In others, it arrives in individual counts like particles hitting one by one. The same photon can even seem to pass through multiple paths at once, as seen in the double-slit experiment. The key insight physicists arrived at is that light is neither purely wave nor purely particle, in the classical sense. Instead, light is described by something called a wave function, which represents probabilities. The wave does not describe physical ripples in space, but the likelihood of detecting a photon in a certain place at a certain time. When no measurement is made, light behaves mathematically like a wave of possibilities. When we measure it, we detect a distinct photon, like a particle. The act of observing collapses the wave of probabilities into a single outcome. This duality challenges our normal thinking. Objects in daily life are intuitively either one thing or another. A stone is solid, water flows, sound vibrates through the air. Light, however, belongs to the quantum world, where our everyday intuitions fail. Richard Feynman emphasized that while the mathematics describing light works perfectly, our brains are not built to imagine what light really is behind those equations. Trying to picture photons as tiny balls or light waves as ripples in a medium always misses something essential. Understanding light's dual nature is not just philosophical curiosity, it forms the foundation for modern technology. Lasers, fiber optic communication, solar cells, medical imaging, and quantum computing all depend on mastering how light behaves as both wave and particle. Engineers and scientists design systems that use interference patterns, photon detection, and probability waves even if the underlying reality remains conceptually strange. Ultimately, the statement that light behaves as both a wave and a particle is a reminder of the limits of common sense. Nature does not always fit the categories we expect. Instead of forcing light into one box, physics developed new concepts that can handle its dual nature. That openness to mystery and precision is what makes the study of light so powerful, and why Feynman believed it represents one of the most fascinating puzzles in science. Richard Feynman believed parts of light's behavior cannot be pictured. Richard Feynman was famous not only for his brilliance, but also for his honesty about the limits of human understanding. When he studied light and quantum mechanics, he reached a bold conclusion. Some parts of how light behaves cannot be pictured in any simple visual way. This was not because scientists were lazy or lacked imagination. It was because the universe itself operates in ways that do not match the mental images our brains evolved to use. From childhood, we learn to understand the world visually. We imagine balls rolling, waves on water, falling apples, spinning tops. These pictures help us predict everyday events. Classical physics also relied heavily on such images. Planets orbit like moving stones, sound travels as vibrating air, and electricity flows like water in pipes. For centuries, scientists expected light to fit one of these familiar categories. Either it was a stream of tiny particles, or it was a smooth wave spreading through space. But quantum physics shattered that expectation. Light sometimes behaves like a particle and sometimes like a wave, yet it is not exactly either. In experiments like the double-slit test, a single photon appears capable of interfering with itself, as if it traveled through multiple paths at once. When no one measures it, light acts as if it explores possibilities. When observed, it snaps into a definite result. That shift does not resemble anything in ordinary life, and there is no simple picture that captures it without distortion. Feynman insisted that pretending to understand through misleading pictures is worse than admitting confusion. He often told students that if they felt the behavior of light seemed mysterious or impossible, then they were finally beginning to grasp how quantum theory really works. He was skeptical of tidy metaphors that make quantum mechanics sound ordinary, because they hide the very strangeness that makes it accurate. To him, honesty about mystery was part of scientific integrity. Instead of pictures, Feynman relied on mathematics. Equations describing light, especially his method called path integrals, predict outcomes with extraordinary precision. They describe light as probabilities, not as solid objects moving along single predictable routes. A photon is represented by a mathematical wave function, giving the chances of finding it in different places. When light interacts with matter, the numbers change, not in a visually intuitive way, but exactly in a way experiments confirm. Feynman emphasized that the success of these equations proves they are telling us something true, even if they resist visualization. He compared this to learning a foreign language. We may not feel it in our bones at first, but with practice we can use it reliably. In quantum physics, the language simply happens to be mathematics instead of mental pictures. Trying to force familiar images onto quantum events, he warned, leads to wrong conclusions. Why can't we picture light accurately? One reason is that our brains evolved to navigate the middle-sized world: rocks, trees, animals, distances we can walk, speeds we can see. The quantum world of photons and electrons is unimaginably small and fast. It follows rules unlike anything we encounter in daily life. Expecting our intuition to work there is like expecting a fish to understand mountain climbing. The fish is not stupid. It is simply adapted to a different environment. Another reason is that visual metaphors always oversimplify. If we draw light as particles, we lose the smooth interference patterns. If we draw it as waves, we lose the fact that detectors register individual photon hits. Each picture explains one behavior while contradicting another. Quantum mechanics forces us to accept that reality is richer than any single mental model. Feynman's honesty was in refusing to pretend that one incomplete picture could stand for the whole truth. Yet Feynman was not pessimistic about this limitation. He believed that mystery is not a wall, it is a doorway. The inability to visualize light fully does not stop science. Instead, it pushes us toward deeper, more precise thinking. The equations allow us to build lasers, transistors, MRI scanners, GPS systems, and countless technologies. We can control light with extraordinary accuracy, even while acknowledging that our intuition lags behind. In Feynman's view, this combination of power and humility is what makes science beautiful. He also believed that curiosity should survive uncertainty. When students asked, "But what is really happening?" he often replied that nature simply behaves this way, and our job is to keep exploring it honestly. Accepting that some parts cannot be pictured does not mean giving up. It means recognizing that understanding can be mathematical, experimental, and predictive, even without perfect mental images. In the end, Feynman's message about light is profoundly human. Our minds crave clear pictures, but the universe is not obligated to match our expectations. By admitting that some aspects of light defy visualization, Feynman invited us into a deeper kind of learning, one that respects both the power and the lie. Myths of human imagination. The mystery remains, not as a failure of science, but as a reminder that reality is larger, stranger, and more fascinating than any picture we can draw in our heads. The double-slit experiment reveals the strangest behavior of light. Among all the experiments ever performed in physics, few are as shocking or as important as the double-slit experiment. Richard Feynman once said that if we truly understood this single experiment, we would understand the heart of quantum mechanics. The reason is simple. The double-slit experiment forces us to confront behavior from light that seems completely impossible according to ordinary logic. Imagine a wall with two very small openings, two slits side by side. Behind that wall is a screen that can record where light lands. If light behaved like tiny bullets, we would expect it to pass through one slit or the other and make two bright spots on the screen. That is exactly what happens with things we understand well, like marbles or grains of sand. They travel straight through whichever opening they choose and pile up behind it. Now imagine light as a wave instead. If we send waves through two openings, like tear waves passing through two gaps in a barrier, the waves spread out and overlap. Where the peaks of the waves meet, they add together and become brighter. Where a peak and a dip meet, they cancel. The result is a striped pattern of bright and dark areas. This is called an interference pattern, and it is unmistakably the signature of wave behavior. When scientists actually performed this experiment with light, they saw interference patterns. Bright and dark bands appeared on the screen, showing that light was behaving like a wave spreading through both slits at once. That was already strange, but still manageable. Perhaps light really was a wave, similar to sound or water. But the true mystery began when scientists made the experiment even more precise. Instead of sending a strong beam of light, they allowed photons to pass through the slits one at a time. Every photon hit the screen individually, like tiny dots appearing. If light were made only of particles, you would expect the dots to collect into two clusters behind the slits. Instead, as more and more single photons arrived, the interference pattern slowly formed again. Somehow, even when photons traveled alone, they buoy. The same striped pattern that waves make. It was as if each photon went through both slits, interfered with itself, and then chose a landing spot based on that interference. But how can one object travel through two paths at once? How can something interfere with itself? These questions stretch common sense beyond breaking. Then came the next twist. Physicists decided to watch what was happening more closely. They added detectors to see which slit each photon actually passed through. The moment they did that, the interference pattern vanished. The photons behaved like normal particles again, producing two clusters instead of many stripes. Simply gaining information about the path destroyed the wave-like pattern. It was not the detector physically blocking light that caused the change. It was the act of measurement itself. When we try to observe which path a photon takes, nature gives us a particle-like answer. When we do not measure, we get a wave-like result. Observation matters in a way that defies everyday experience. What the double-slit experiment reveals is that light cannot be described using just one picture. It is not simply a wave traveling smoothly, nor is it a tiny particle flying through space. Instead, quantum theory tells us that light exists as a spread-out wave of probability before we measure it. That probability wave describes where the photon might appear. When a measurement is made, the wave collapses and the photon shows up in one definite spot. The stripes on the screen reflect the underlying probability wave, even though each photon arrives as a single point. The experiment does not just challenge our understanding of light, it challenges our idea of reality itself. We are forced to ask, what does it mean for something to exist as a possibility rather than a solid object? Does reality depend on observation? Do photons decide their behavior based on whether we look? Scientists are careful with such philosophical questions, but one thing is clear. Classical ideas fail here. Our usual intuition, shaped by everyday objects, simply does not apply. The double-slit experiment shows that quantum systems obey rules that are deeply unfamiliar, yet incredibly precise. They may look mysterious, but the mathematics predicts them perfectly. Far from being only a curiosity, this experiment laid the foundation for modern technologies. Quantum mechanics, the theory needed to explain the double-slit experiment, powers lasers, transistors, atomic clocks, and even emerging quantum computers. By accepting the strangeness instead of rejecting it, science unlocked entirely new capabilities. The double-slit experiment remains powerful because it forces us to be humble. It reminds us that the universe is not obligated to behave in ways our minds find comfortable. What looks impossible from a common-sense perspective can still be true, and can still be measured, tested, and used. In that sense, the double-slit experiment is not just about light, it is about our relationship with knowledge. It teaches that curiosity sometimes requires letting go of simple pictures and trusting careful evidence instead. And like Feynman said, once we face this experiment honestly, we glimpse the true depth and wonder of quantum reality. Particles of light seem to interfere with themselves. When we talk about everyday objects, the idea that something could interfere with itself sounds impossible. A single car cannot block its own path on the road. A single raindrop does not collide with itself in the sky. Things we see and touch follow simple, straightforward rules. They occupy one place at a time and move along one path. But when scientists studied light at the quantum level, they discovered behavior that breaks this intuition completely. Photons, the tiny particles that make up light, behave as if each one can read out, travel through multiple routes at once, and interfere with its own possibilities. The clearest example of this strange behavior appears in the famous double-slit experiment. When photons are sent one at a time toward two narrow slits, they do not simply produce two clusters of impacts on the screen behind them. Instead, over time they form a pattern of alternating bright and dark bands. The same kind of pattern produced by overlapping waves. This suggests interference is taking place. But since only one photon is traveling at a time, there is nothing else for it to interfere with. The only conclusion that fits the data is that each individual photon somehow interferes with itself. To understand what interference means, think of ripples on water. When two sets of ripples meet, there are regions where they add up and become taller, and regions where they cancel and become flat. Light behaves similarly in this experiment, except that it does so even when only a single photon is present. Where the underlying wave pattern predicts strong intensity, photons appear more often. Where the wave pattern predicts cancellation, photons rarely appear at all. This leads us to a deeper concept. Before being detected, a photon is not a tiny marble traveling along a single track. Instead, Quantum physics describes it as a wave of probability. That wave extends through space and represents all the possible paths the photon might take. When it approaches the double slits, the probability wave passes through both openings and spreads out on the other side. The two parts of the wave then overlap and interfere, creating a pattern of higher and lower probabilities. When the photon is finally detected on the screen, it appears at one definite point, but the chances of where that point will be depend on the interference pattern of its own probability wave. Richard Feynman explained this using his sum over histories idea. According to this view, the photon does not commit to a single path. Instead, nature behaves as if the photon explores every possible route from the source to the detector. Each possible path contributes to the final probability of detection. Some paths cancel each other out, while others reinforce each other. The interference pattern we see is the result of these overlapping possibilities, even though we eventually observe only one outcome. This explanation may sound like science fiction, but it is supported by precise experiments. Physicists have slowed light down, sent photons through more complicated arrangements, and even used electrons, which have mass, in similar setups. Every time, the same conclusion appears: quantum particles behave as if they exist in many possible states at once, until a measurement forces a single result. Interference is not a trick of equipment, it is a genuine feature of nature. The natural question people ask is, what is the photon really doing when we are not measuring it? Does it split into pieces? Does it become a ghostly cloud? Or is it simply a mathematical idea with no physical reality? Here is where Feynman's humility becomes essential. He argued that trying to imagine a classical picture leads us astray. There is no simple, everyday analogy that fits entirely. The safest statement is that light behaves in a way that can only be accurately described by quantum mathematics. Anything beyond that is just a story we tell ourselves. Another striking feature emerges when scientists try to catch the photon in the act. If detectors are placed at the slits to determine which one the photon goes through, the interference disappears. The photon behaves as though it travels through only one slit, and the striped pattern vanishes. By gaining information about the path, we erase the conditions required for self-interference. In quantum mechanics, knowledge and behavior are mysteriously linked. This does not mean consciousness controls reality in a mystical way, but it does mean that measurement becomes part of the physical process. Understanding that photons interfere with themselves has changed technology and philosophy alike. Devices such as interferometers, lasers, and quantum communication systems rely on controlling interference precisely. Engineers can exploit the wave-like nature of individual particles to achieve results impossible in classical systems. At the same time, philosophers and scientists continue to debate what this means for our understanding of reality. Are particles real before observation, or are they just potential outcomes? What remains certain is that the phenomenon of self-interference forces us to rethink simple ideas about objects and motion. A photon is not confined to the familiar rules of everyday matter. It lives in the quantum realm, W. Here, probability replaces certainty, and where possibilities behave as if they are real enough to influence one another. In that realm, the statement that a particle of light interferes with itself is not poetry. It is a precise description of what experiments reveal. In the end, this behavior does not make the universe chaotic. On the contrary, it shows that nature follows elegant, consistent laws that simply lie outside our common intuition. The mystery invites humility and curiosity. Light reminds us that the world is far richer than the pictures we can easily imagine, and that even a single photon carries with it a doorway into the strange, beautiful logic of quantum physics. Observation changes the outcome of experiments with light, one of the most unsettling discoveries in modern physics is the idea that observation can change what happens in an experiment with light. At first, this sounds impossible. We are used to thinking of observation as passive. Looking at a tree does not change the tree. Watching a train rush past does not change its speed. In everyday life, we believe the world goes on independently of whether we are watching or not. But in the quantum world, the world of photons and electrons, things work differently. When we observe light, the very act of measuring it becomes part of the event and alters the result. This idea is most clearly illustrated through experiments like the double-slit test. When light passes through two slits without being observed, it forms an interference pattern, the hallmark of wave behavior. Yet when detectors are dead to determine which slit the photon goes through, the interference disappears. Light suddenly behaves like particles traveling through only one slit. Nothing else in the experimental setup changes except the measurement itself. That simple addition of watching transforms the outcome. Why does this happen? The reason lies in how quantum systems exist before measurement. In classical physics, an object has definite properties at all times: position, speed, path. In quantum physics, particles like photons exist in a superposition, meaning they occupy multiple possible states at once. Instead of having one precise path, the photon is described by a probability wave spread over many potential paths. This wave is not just ignorance on our part, it is the actual physical description of the system. When we measure the photon, the probability wave collapses into a single definite result. We no longer see many possibilities. We see one outcome, one location, one path recorded by our detector. That collapse is directly triggered by observation. Without measurement, the wave behaves freely, creating interference. With measurement, the wave loses its ability to overlap and instead resolves into a single event. Observation is not passive, it defines which aspect of light shows itself. Richard Feynman and other physicists were careful to emphasize that this does not mean human consciousness magically controls reality. The effect occurs whether detectors are operated by people, computers, or automatic devices. Observation, in physics, simply means interaction with a measuring instrument that extracts information about the system. When photons interact with detectors, atoms, or even stray particles in the environment, their quantum state changes. Gaining information comes with a physical cost. It destroys superposition and forces one outcome. This principle is called the measurement problem, one of the greatest puzzles in quantum theory. It raises questions that touch both science and philosophy. What exactly counts as a measurement? At what moment does the wave collapse? Is the world made of possibilities until something records them? Different interpretations of quantum mechanics answer these questions in different ways, but they all agree on one undeniable fact: observations change results. The effect has been tested repeatedly and in increasingly sophisticated ways. Experiments have shown that even when detectors are placed after light has already passed the slits, the pattern on the screen still depends on whether measurement occurs. Quantum eraser experiments demonstrate that if path information is removed or erased after being collected, the interference pattern can reappear. These results are deeply counterintuitive, yet they consistently match the mathematical predictions of quantum theory. The core lesson is that light does not behave as a fixed object waiting to be discovered. It behaves as a set of possibilities that solidify only when measured. Observation is part of the machinery of nature, not merely a spectator's action. In the quantum world, there is no clean separation between the experimenter and the experiment. The measuring device and the particle become entwined, and the outcome emerges from that interaction. This discovery has profound technological implications. Devices like quantum cryptography systems depend on the fact that observation disturbs quantum states. If someone tries to spy on a quantum communication channel, their measurement inevitably changes the signal and reveals their presence. Quantum computing also relies on controlling superposition carefully while delaying measurement until the final stage. Harnessing the sensitivity of quantum states allows us to build tools more powerful and secure than anything classical physics could provide. At the same time, the idea that observation alters reality forces us to reconsider what we mean by objectivity. Science once seemed like a window thaw, or which we simply viewed the world as it is. Quantum theory shows that at the deepest level, observing is more like touching than seeing. We cannot probe the quantum realm without disturbing it. Instead of giving up, physicists embraced this limitation, built it into their equations, and discovered that nature still behaves lawfully, just not in ways that match our intuition. Ultimately, the fact that observation changes experiments with light is not a flaw or a mistake. It is a fundamental feature of the universe. It reminds us that knowledge always comes with interaction, and that the smallest building blocks of reality operate by rules different from the familiar world around us. Rather than weakening science, this insight has strengthened it, enabling extraordinary precision and breakthroughs. The mystery remains powerful because it humbles us. Light teaches that the boundary between watcher and world is thinner than we once believed, and in that delicate boundary, where measurement meets possibility, we find both the strangeness and the beauty of quantum physics. Quantum mechanics describes light using probability, not certainty. In everyday life, we expect events to follow clear, predictable rules. If you throw a ball, you can trace its path through the air. If you roll a marble across the floor, you can calculate how far it will travel before stopping. Classical physics, the science that explains cars, planets, and bridges, is built on certainty. It assumes that if we know enough about an object's starting position and speed, we can predict exactly what will happen next. But when scientists began studying light and matter at extremely small scales, those rules broke down. Light, made of tiny particles called photons, did not act like miniature versions of everyday objects. Instead, it behaved in a way that seemed unpredictable, as if nature itself was dealing in chances rather than guarantees. To explain this strange behavior, physicists develop quantum mechanics, a theory where probability sits at the center, not certainty. In quantum mechanics, light is described by something called a wave function. This wave function is not a physical wave in space like ripples on water. Instead, it represents the probabilities of finding a photon in different places or states. The wave function tells us the likelihood that a photon might appear here rather than there, or behave this way rather than that way. Until a measurement is made, the photon does not have one definite position or path. It exists in a superposition of possibilities. This is very different from classical thinking. In classical physics, uncertainty usually means ignorance. If you do not know where a car is, it is because you did not look, not because the car itself CKS position. But in quantum mechanics, uncertainty is built into reality. The photon genuinely does not have a fixed position until it is detected. The famous Heisenberg uncertainty principle expresses this idea mathematically. Certain properties, such as position and momentum, cannot both be known exactly at the same time. The more precisely we measure one, the less precisely the other can be defined. Richard Feynman and other quantum pioneers embraced this radical shift. Instead of asking, "Where is the photon right now?" they asked, "What is the probability that the photon will be detected in a particular place?" The answers came in the form of precise equations that matched experiments perfectly. Light was no longer described as something with predetermined behavior. It was described as a system of probabilities that become real outcomes only when observed. The double-slit experiment provides a powerful example. When photons pass through two slits, quantum mechanics does not say, "This photon definitely went through the left slit," or "It definitely went through the right slit." Instead, it gives a probability distribution, showing the chances of different outcomes. The reference pattern formed on the screen reflects this distribution. Bright areas represent high probability, while dark areas represent low probability. Each photon lands in a specific spot, but the pattern of many photons follows the wave of probabilities predicted by the equations. This approach might sound like a mathematical trick, but it is more than that. Quantum probabilities are not like Ling dice. Dice are unpredictable because we lack full information about how they are thrown. In contrast, quantum probabilities seem fundamental. Even if we know everything possible about a photon, we still cannot predict its exact landing point, only the probability of each possible landing point. Nature itself leaves room for genuine chance at the smallest level. Some scientists once hoped T-hat hidden variables might explain everything, unseen factors that secretly determine outcomes. But decades of experiments, including tests of Bell's theorem, showed that no simple hidden mechanism can fully restore classical certainty. The universe truly behaves in a probabilistic way, connected across distances and events in ways that defy older expectations. This probabilistic view is not a weakness. In fact, it is incredibly powerful. Quantum mechanics produces some of the most accurate predictions in all of science. The behavior of atoms, lasers, semiconductors, and even stars relies on probability-based equations. Without quantum mechanics, there would be no modern electronics, no MRI scanners, no GPS accuracy, and no emerging quantum computing industry. Still, the idea that light is governed by probability challenges our intuition. We like to imagine that reality is fixed and definite at every instant. Quantum mechanics suggests a subtler picture. Reality unfolds as a set of possibilities that solidify only when interactions take place. Feynman encouraged students to accept this without forcing it into classical categories. He argued that insistence on certainty comes from habit, not necessity. Nature simply works differently at microscopic scales. At a deeper level, this understanding reshapes our concept of knowledge. Instead of expecting absolute predictions, we learn to think in distributions, likelihoods, and ranges. We recognize that science is not just about declaring exact outcomes, but about describing patterns of possibility with precision. Quantum mechan. ICS shows that uncertainty and reliability can coexist. Uncertainty in single events, reliability in overall patterns. In the end, describing light through probability is not a sign of confusion. It is a reflection of how the universe truly behaves. The rules may be strange, but they are consistent and measurable. The mystery is not a failure of explanation. It is a window into a reality more BTLA than our everyday experience. Light teaches us that certainty is not always the foundation of truth. Sometimes, the deepest understanding comes from accepting probability as part of the structure of nature itself, and appreciating the remarkable accuracy with which quantum mechanics captures that structure. Light exchanges energy in tiny packets called quanta. When most people think about light, they imagine it as smooth and continuous, like sunlight pouring through a window or the steady glow of a lamp. For centuries, scientists thought the same. They believed light delivered energy the way water flows from a faucet. More flow meant more energy, less flow meant less. But when researchers began to examine light at extremely small scales, they discovered something astonishing. T does not deliver energy smoothly. Instead, it exchanges energy in tiny, indivisible packets called quanta, and each packet is a photon. This idea marked the birth of quantum theory, and it completely changed physics. The mystery first appeared in the late 1800s. Scientists were studying how hot objects glow, from heated metal to stars in the sky. Classical physics predicted that as objects became hotter, they should emit infinite energy at short wavelengths, something known as the ultraviolet catastrophe. But that clearly did not happen. Nature behaved differently. In 1900, Max Planck proposed a radical solution. He suggested that light wasn't emitted in any amount we wished. Instead, it was released in small, fixed bundles of energy. The energy of each bundle depended on the R, or frequency, of the light. High-frequency blue and ultraviolet light carried larger packets. Low-frequency red light carried smaller ones. This solved the puzzle and opened a new world. A few years later, Albert Einstein pushed the idea further. He argued that light wasn't just emitted in quanta, it exists as quanta. Each packet became what we now call a photon. In Einstein's explanation, the photoelectric effect, light shining on a metal could knock electrons loose only if its photons carried enough energy. Increasing brightness did not help if the color frequency was too low. Energy came not as a stream of continuous waves, but as discrete hits. This changed everything. Light now behaved like both a wave spreading and interfering and a particle delivering quantized energy. The dual nature was unavoidable. Why does quantized energy matter so much? Because it explains how light interacts with matter. Atoms, electrons, and molecules also behave in quantized ways. Electrons can only occupy specific energy levels, not the spaces in between. When a photon hits an atom, it can only be absorbed if its energy matches one of those allowed jumps. If the energy is wrong, the photon simply passes by. This is why elements emit and absorb light in specific colors, forming beautiful spectral lines scientists use to identify stars billions of light years away. It also explains why objects glow in certain temperatures. A heated stove doesn't smoothly turn from dark to bright. It shifts from dull red to orange to white because the distribution of photon energies changes. As atoms vibrate faster, behind every glow is the quantum rule: energy moves in steps, not slopes. Richard Feynman admired this idea because it showed how nature hides complexity behind simple mathematical rules. A photon doesn't gradually share energy. It's all or nothing, like a coin instead of liquid. Yet when trillions of photons act together, the world looks smooth to us. We see steady beam and soft light, unaware of the tiny packets racing through space. Another fascinating feature is that each photon travels at the speed of light and carries momentum even though it has no mass. When sunlight hits a spacecraft, it pushes ever so gently. Engineers now design solar sails that ride this photon pressure, letting spacecraft travel without fuel. This is a direct consequence of light. Quantized nature. At the same time, photon energy explains why ultraviolet light can burn skin while visible light usually cannot. Ultraviolet photons carry higher energy packets, enough to damage DNA. Visible light photons simply lack the punch. Brightness doesn't change the power of each packet, it only increases the number of packets arriving per second. The quantization of light also the foundation for modern technologies. Lasers work by forcing atoms to release photons of exactly the same energy and phase, producing beams of incredible precision. Solar panels function because photons transfer their quantized energy to electrons, generating electric currents. Even emerging quantum computers rely on controlling individual photons and their energy states. But the concept remains philosophically unsettling. If light is a wave spreading through space, how can it deliver energy in perfect little bundles? And if it is a stream of particles, how does it interfere like ripples on water? The truth, as quantum mechanics shows, is that light is neither of our simple categories. A photon is not a tiny billiard ball or a classical wave. It is a quantum object described best by probability and energy quanta. Our brains crave solid pictures, but nature offers mathematical rules instead. Rules that work with astonishing precision. Feynman often said that we should not pretend light behaves like anything familiar. Instead, we should accept that photons follow quantum laws, even when those laws feel strange. The quantization of light is a reminder that reality is built from discrete building blocks, sudden jumps, exact packets, specific transitions, wrapped inside behavior that often looks smooth from far away. In the end, the discovery that light exchanges energy in quanta did more than solve a physics puzzle. It revealed a deep structure within the universe. From the glow of stars to the screens in our hands, everything involving light operates through these tiny packets. The mystery remains beautiful, simple, precise, and profoundly different from the world our senses were built to understand. Scientists rely on equations when visual imagination breaks down. When people first begin learning science, they usually imagine that the goal is to picture how things work. We draw diagrams of atoms, we sketch waves and orbits, and we imagine tiny balls coal. I ding when we think about particles. These pictures are helpful, but they are also limited. As scientists push deeper into the microscopic world, especially the world of light and quantum physics, they reached a point where the pictures no longer matched reality. At that point, equations became the more reliable guide. Richard Feynman emphasized this over and over. He knew that our brains, Evo, live to handle everyday objects, stones, rivers, people, and simple motions. But light, electrons, and quantum fields do not behave like everyday objects. Trying to create a neat mental picture can actually mislead us. The equations, however, do not care about our intuition. They simply describe what nature does, even when it feels strange. Take the example of light behaving both as a wave and a particle. If we try to imagine it as only one thing, our logic quickly collapses. A wave spreads out everywhere, but a particle strikes in one exact spot. Which picture is correct? Neither, and both. The mathematical description, the wave function, carries the information about probabilities, while the act of detection shows up as a single particle-like outcome. No drawing on paper fully capture that dual role. The equation does. Equations let scientists work with relationships that cannot be visualized. Probabilities adding and cancelling, phases rotating in abstract spaces, and quantities existing in superposition. These are not things we can see, yet they describe the world incredibly accurately. When physicists compute where interference bands will appear, or how likely a photon I to be detected in a certain spot, they rely on formulas that work every time. If they tried to replace those formulas with mental pictures, experiments would quickly prove them wrong. This may sound cold or mechanical, as if science becomes only math and no imagination. But something interesting happens instead. Equations become a different kind of imagination, a symbolic one, a skilled physic. IST can see meaning inside mathematical expressions the way a musician hears structure inside sheet music. The symbols reveal patterns, symmetry, conservation, resonance, and probability. Those patterns are often more trustworthy than any picture. Consider the double-slit experiment again. A simple drawing might show two slits and waves spreading like ripples. That picture helps, but it also hides the most important truth. The interference pattern is produced by probability amplitudes adding and cancelling. These amplitudes are complex numbers, not visible quantities. Only their squared magnitudes become visible as bright and dark bands. You cannot sketch complex numbers interacting. You must calculate them. The calculation explains the pattern precisely, even if the mind cannot visualize what is happening in between. This is why Feynman said certain aspects of quantum behavior have no visual explanation. He did not mean they are magical or unknowable. He meant the correct explanation is mathematical, not pictorial. Whenever people insist on forcing a visual model, like imagining photons, choosing paths as if they were tiny decision-making insects, they eventually bump into contradictions. The math never bumps into contradictions when used correctly. It simply matches nature. Reliance on equations also protects science from personal bias. Each of us carries mental habits shaped by culture, language, and experience. Two people might imagine the same phenomenon in completely different ways, yet both might insist their picture is the right one. Equations do not argue, they give clear predictions. If the result disagrees with experiment, scientists know the equation must be changed. If it succeeds again and again, confidence grows, even if nobody can draw an intuitive picture. Some people find this unsatisfying. They want the comfort of imagining physical reality the way they imagine a movie scene. But history shows that clinging to comforting pictures can slow progress. Early scientists resisted the idea that planets do not follow perfect circles, because circles felt natural. They resisted relativity because the idea of time bending was impossible to visualize. Over time, equations guided them to truths beyond intuition, and only later did new metaphors slowly form around those truths. The lesson is not that imagination is us. Less. It is that imagination must be disciplined by mathematics. Pictures are starting points, bridges into difficult ideas. Equations are the tools that verify which parts of those pictures are real and which parts are illusions. When light behaves in ways that confuse us, the safest path is to trust what the calculations reveal and let our intuition catch up gradually. In this sense, equations become a language spoken directly between the human mind and nature. They translate mysteries into precise statements: how strong, how likely, how fast, how far. Feynman admired this deeply. He believed we should marvel not only at the strange behavior of light, but also at the astonishing fact that human beings can write symbols on paper and predict what the universe will do. So when scientists say they rely on equations where visual imagination fails, they are not giving up. They are choosing accuracy over illusion. They are acknowledging that the universe is allowed to be stranger than our instincts. And they are trusting a method that, despite its abstractness, has built lasers, computers, satellites, and technologies that shape modern life. The math works, and in science that is the closest thing we have to truth. This mystery changes how we understand reality itself. When people first learn about light and quantum mechanics, they often think it is simply a strange branch of physics. But the more deeply you look, the more you realize that it does not just describe light differently, it challenges our entire concept of what is real. The mystery surrounding light forces us to reconsider what it means for something to exist, to move, and to be observed. For most of human history, reality seemed straightforward. Objects existed in definite places. Causes produced clear effects. If something happened, it was because something else pushed it, pulled it, or acted upon it. This worldview worked beautifully for everyday life and classical physics. It helped explain falling apples, moving planets, and flowing rivers. Reality appeared solid, predictable, and intuitive. Then scientists began studying light at very small scales, and the old picture cracked. Light behaves in ways that refuse to fit into one category. It arrives in discrete packets called photons, suggesting particles. Yet it spreads out and interferes like a wave. When we measure it, it gives definite answers, but before measurement, it seems to exist only as a cloud of probabilities. The very act of observing changes the outcome. Suddenly, reality is no longer something that simply is. It becomes something partly shaped by interaction. This is a radical idea. In classical thinking, observation is passive. Whether you look at a tree or not, the tree remains the same. In quantum physics, observation is active. Measuring light is not like looking at a tree. It is more like participating in the process that determines the result. Reality at the smallest level is not fully decided until something interacts with it. That does not mean consciousness magically controls the universe, as popular myths sometimes claim, but it does mean that physical processes of measurement play a role in what becomes real. Another profound shift involves certainty. In classical reality, if we knew enough information, we could predict everything exactly. Quantum mechanics destroys that dream. Light obeys strict laws, but the laws themselves are probabilistic. They do not tell us where a photon will land. They tell us the chances. We can predict patterns, not individual outcomes. Feynman and other physicists accepted this not as a temporary gap in knowledge, but as a fundamental feature of nature. This raises deep questions. Is reality fundamentally uncertain? Are possibilities as real as outcomes until something selects among them? The mystery of light also challenges our sense of locality, the idea that things only affect one another when they are close by. Quantum phenomena show correlations between particles that remain linked across vast distances. Although no information travels faster than light, the connection still exists in a way that classical logic struggles to explain. The universe behaves like a single, deeply connected system, not just a collection of isolated pieces. Then there is the issue of representation. For centuries, science assumed that if we worked hard enough, we could picture reality. Quantum mechanics shattered that confidence. We discovered that the universe operates in ways that cannot be fully pictured in human imagination. The best representation is not a mental image but an equation. Reality becomes mathematical before it becomes visual. That realization alone changes philosophy, science, and even how we think about knowledge. Another transformation concerns our role in the universe. Older science placed humans as observers standing outside nature. Quantum physics puts us back inside the system. Our instruments, our experiments, and our questions influence what we see. We are not spectators watching a pre-written movie. We are part of the unfolding script, governed by the same mysterious laws as everything else. This mystery also reveals something humbling. Nature is not obligated to match our expectations. Light obeys rules far deeper than intuition. Whenever human imagination clashes with experimental results, nature wins. Instead of forcing reality to fit our mental models, we must expand our models to fit reality. That mindset, humility combined with curiosity, is one of the greatest gifts of modern physics. Finally, the mystery invites wonder. Instead of seeing the universe as a simple machine, we begin to see it as layered, subtle, and full of surprises. Light is not just illumination for our eyes, it is illumination for our thinking. It reveals that certainty has limits, that observation matters, that mathematics can describe truths beyond imagery, and that reality is richer than any single description. So when we say this mystery changes how we understand reality, we mean it in the deepest sense. It alters our philosophy, our science, and our self-perception. It teaches us that reality is not always what it appears to be, and that understanding sometimes requires accepting strangeness rather than eliminating it. Instead of closing doors, the mystery of light opens them, inviting us to company. Exploring, questioning, and marveling at a universe far more intricate than we ever imagined. The mystery invites curiosity rather than simple answers. When people first hear that light behaves in mysterious ways, that it is both wave and particle, that observation affects outcomes, that even Feynman said it has no true visual explanation, some feel uneasy. They want clarity. They want final answer that explains everything neatly. But the story of light shows something deeper. Not every mystery exists to be solved in a single sentence. Some mysteries exist to draw us further in, to make us ask better questions, and to expand our way of thinking. The mystery of light does exactly that. Science is often misunderstood as a giant book of final answers. In reality, science is like an endless conversation with nature. Every time we learn something new, new questions appear. Light proves this beautifully. When Newton studied light, he discovered how it bends and reflects, and people thought the puzzle was finished. Then scientists discovered interference, diffraction, and color as waves, and they thought the puzzle was finished again. Later, quantum physics revealed photons and probabilities, and once again, certainty slipped away. Each stage did not erase the previous knowledge, it deepened it. The mystery didn't vanish, it evolved. This should change how we react to mystery. Instead of demanding instant closure, we learn to appreciate the role of curiosity. Curiosity does not simply ask, "What's the answer?" It asks, "What else can this teach us? And what might we be missing?" That attitude is powerful. Without it, science would have stopped long ago. Feynman himself often celebrated not knowing. He believed that being comfortable with uncertainty is a sign of strength, not weakness. When scientists say, "We don't fully understand this yet," they are not admitting defeat. They are opening a door. Mystery becomes motivation. It drives experiments, sparks ideas, and inspires generations of learners. Children are often natural scientists because they constantly ask why. The mystery of light invites adults to rediscover that same curiosity. Curiosity also protects us from oversimplification. The universe is not obligated to fit into quick RK answers. When someone insists on one tidy explanation for quantum behavior, they usually end up replacing truth with comforting stories. Instead, curiosity keeps our minds open. It lets us explore math, experiment design, philosophy, and technology together. It reminds us that multiple perspectives can coexist, each revealing part of a larger picture. The mystery of light also encourages humility. Thank you. Humanity has built telescopes that reach galaxies and microscopes that reveal atoms, yet we still encounter questions we cannot fully picture. Instead of feeling frustrated, we can feel inspired. If something as common as light still holds secrets, imagine how much more remains to discover. Curiosity transforms confusion into wonder. It shifts the question from, "Why don't we know everything?" to how incredible that there is still so much left to learn. Another important effect is creativity. Mysteries force us to invent new tools, new ways of thinking, and even new mathematics. Many technologies, lasers, fiber optics, quantum computing, medical scanners, grew from scientists asking curious questions about strange light experiments. If researchers had simply shrugged and said, "TS is weird, but let's not dig deeper," those modern tools would not exist. Curiosity, not certainty, made progress possible. The mystery also teaches patience. Some questions take decades or centuries to answer. That doesn't make the search pointless. It means knowledge builds layer by layer. A student reading about photons today contributes to a history of inquiry stretching back centuries. Someday, that same student might be part of the next breakthrough. Mystery creates continuity between generations, a shared quest. There is also a personal side to all of this. Learning about the strange nature of light can change how we think about learning itself. Instead of fearing difficult subjects, we learn to sit with them, explore them, and grow through them. Curiosity becomes a habit. It seeps into how we question the world, how we solve problems, and how we think about truth. We stop seeing knowledge as a finish line and start seeing it as a journey. Most importantly, the mystery of light invites us to feel awe. Not the kind of awe that shuts down thinking, but the kind that inspires deeper thinking. When we realize that something as ordinary as a beam of sunlight contains phenomena beyond visualization, logic, and expectation, we begin to see the universe differently. We live inside something grand, layered, and endlessly surprising. That realization alone is worth cherishing. So when we say the mystery invites curiosity rather than simple answers, we recognize that uncertainty is not a failure of science. It is its engine. The unknown pulls us forward. It challenges our assumptions. It trains us to ask sharper, more meaningful questions. Light, with all its strangeness, becomes a teacher. It whispers that there is always more to discover, and that curiosity is the spark that keeps discovery alive.